Okay, so this is Unit 3, Section 14.7, Maximum and Minimum Values. In this section, we're going to see how to use partial derivatives to locate maxima and minima of functions of two variables. So look at the hills and valleys in the graph of f as shown in Figure 1. There are 2 points, A and B, where our function values are going to be greater than our nearby values of x and y. The larger of these two values is the absolute maximum. Likewise, f has 2 local minima where our f of AB is going to be smaller than our nearby values. The smaller of these two values is the absolute minimum. So this leads to 2 definitions. We know that a function of two variables has a local maximum at A and B if our function value xy is less than or equal to f of AB when xy is near AB. This means that our function f of xy is less than or equal to our function at AB for all points xy in some disk with a center A. So for all points xy in some disk with center AB. The number is then going to be called a local maximum. If our function value is greater than f of AB when xy is near and again that would be defined on a disk, then f has a local minimum and f of AB is a local minimum value. If the inequalities in definition 1 hold for all points f xy in the domain of f, then f has an absolute maximum or an absolute minimum at AB. So here is the maximum portion part of the definition. So theorem 2 says that if f has a local maximum or a minimum at A and B, and the first order of partial derivatives exists there, then our partial derivative with respect to x at AB is equal to 0, and the partial derivative of y at AB is equal to 0. A point AB is called a critical point or a stationary point of f if the partial derivative of f with respect to x of AB equals 0 and the partial derivative of y of AB equals 0, or if one of those partial derivatives does not exist. Theorem 2 then says that if f has a local maximum or a minimum, then AB is then a critical point. However, as in single variable calculus, not all critical points will give rise to maxima or minima. At a critical point, a function could have a local maximum, a local minimum, or neither. And take a look at example 1. We have f of xy is x squared plus y squared minus 2x minus 6y plus 14. So we know that our partial derivative with respect to x is going to be 2x minus 2. And our partial derivative with respect to y will be 2y minus 6. If we set these partial derivatives equal to 0, then we have 2x minus 2 equals 0, and that happens when x equals 1. And we set f of y equal to 0, and so 2y minus 6 is equal to 0. And then we have that y equals 3. So therefore, the only critical point that we have then is going to be 1, 3. So to find that point, let's go ahead and solve f of xy. We have x squared, and I'm going to rearrange this, minus 2x plus y squared minus 6y plus 14, and we're going to go ahead and complete this complete the square. So we take negative, and we're going to complete the square within on one side. So we have negative 1 squared, so that's going to be plus 1. Take negative 3 squared, we're going to add 9, and so we need to subtract 1 and subtract 9. And so we end up with f of xy is going to be, and let's go ahead and write this, x minus 1 quantity squared plus y minus 3 quantity squared plus 4. Since we know that x minus 1 quantity squared is greater than or equal to 0, and y minus 3 quantity squared is greater than or equal to 0, we have then that f of xy will be greater than or equal to 4 for all values of x and y. Therefore, we have that f of 1, 3 equals 4 is a local minimum, and in fact, it is the absolute minimum of f. And this could be confirmed geometrically from the graph of f, which we know is an elliptic paraboloid with the vertex 1, 3, and 4. The following test is analogous to the second derivative test for functions from single variable calculus. So this is the second derivative test for multivariable. Suppose that the second partial derivatives are continuous on a disk with center AB, and suppose that the partial with respect to x at AB is equal to 0, and the partial of y with respect to partial of f with respect to y at AB is equal to 0, which means then that AB is a critical point of f. We're going to define D as a function of AB, where it is the second partial of f with respect to x evaluated at AB times the second partial of f with respect to y at AB minus our mixed partial at AB quantity squared. If D is greater than 0 and our second partial with respect to x is greater than 0, then we have a local minimum. If D is greater than 0 and our second partial with respect to x at AB is less than 0, then we have a local maximum. If D is less than 0, then f of AB is neither a local maximum nor a local minimum. In case C, point AB is called a saddle point of f, and the graph of f crosses its tangent plane at A and B. So for a function of one variable, the extreme value theorem says that if f is continuous on a closed interval, then f has an absolute minimum and an absolute maximum. So remember, f of x is continuous on a closed interval, then f of x has an absolute max and an absolute min. According to the closed interval method, we found these by evaluating f not only at the critical numbers, but also at the endpoints of A and B. There is a similar situation for functions of two variables. Just as a closed interval contains its endpoints, a closed set in R squared is one that contains all of its boundary points. So a boundary point of D is a point on AB such that every disk with the center AB contains points in D and also points not in D. So for example, if we have D is defined as our function of xy such that x squared plus y squared is less than or equal to 1, that consists of all points on or inside the circle x squared plus y squared equals 1. And this is defined as a closed set because it contains all of its boundary points, which are the points on the circle x squared plus y squared equals 1. So let's look at some pictures here. If one point on the boundary curve were omitted, the set would be not closed. So for example, in figure 11a, we have closed sets. Figure 11b, we have sets that are not closed, where in this circle, this would be an x squared plus y squared is less than or equal to r squared. The second circle is just leaving out one point, and then notice that this line here on this square is solid while the remaining ones are dotted. So a bounded set in R squared is one that is contained within some disk. In other words, that boundary is going to be finite in extent. Then, in terms of closed and bounded sets, we can state the following counterpart of the extreme value theorem in 2 dimensions. If f is continuous on a closed and bounded set and we're going to put this as r squared, then f will attain an absolute maximum value, f of x1, y1, and an absolute minimum value, f of x2, y2, at some given points, x1, y1, and x2, y2, in our bounded set D. To find the extreme values guaranteed by Theorem 8, we note that by Theorem 2, if f has an extreme value at x1, y1, then x1, y1 is either a critical point of f or a boundary point of D. So, thus we have the following extension of the closed interval method. To find the absolute maximum or absolute minimum values of a continuous function on a closed and bounded set, you have the following steps. 1, find the values of f at the critical points. 2, find the extreme values of f on the boundary of D. The largest of these, and then we'll state, compare. The largest of these values from steps 1 and 2 are the absolute maximum, and the smallest of these values is the absolute minimum. Then we're going to find the absolute maximum and minimum values of the given function x squared minus 2xy plus 2y on the rectangle defined by D, where x ranges from 0 to 3 and y ranges from 0 to 2. So, since f is a polynomial, we know that it's continuous on the closed and bounded rectangle. So, f of xy is continuous on D. Therefore, Theorem 8 tells us that there is both an absolute maximum and an absolute minimum. So the first thing is to find the critical point. So we need our partial derivative with respect to x is going to be 2x minus 2y, and our partial derivative with respect to y is going to be negative 2x plus 2. We need to set both of these equal to 0. And we have so from there we can see that we have that x is going to be 1, which means then y will equal 1. So our only critical point on this is 1, 1. And the value at 1, 1 is then going to be 1. So step 2, we need to look at the values of f on the boundary of D, which consists of the 4 line segments as shown in figure 12. On L1, we have that y equals 0. So therefore our function is just going to be x squared, where x ranges from 0 to 3. This is an increasing function of x, so its minimum value is going to be f of 0, 0, which is 0, and its maximum value is going to be f of 3, 0, which is going to be 9. So then we move on to L2. So for L2, we have the function x equals 3, and so our f of xy becomes f of 3y, and we end up with 9 minus 4y, where y is ranging from 0 to 2. We can see that this is a decreasing function of y, so its maximum value is going to be f of 3, 0 is equal to 9, and its minimum value will be f of 3, 2, which will be 1. So next line we look at is going to be L3, and we have that line is going to be y equals 2. So then our function of xy becomes f of x2, and we have x squared minus 4x plus 4, where x ranges from 0 to 3. Simply by observing that we can rewrite this function as x minus 2 quantity squared, we can see that the minimum value of this function is going to be at 2, 2 is equal to 0, and the maximum value of this function is going to be at 0, 2, and is going to be 4. Finally, on L4, we have that x equals 0, and so we have our function f of 0y is going to be 2y, where y ranges from 0 to 2, and then we have a maximum value, f of 0, 2 will be 4, and f of 0, 0 is going to be 0. So therefore, on the boundary, the minimum value of f is 0, and the maximum is 9. So in step 3, we compare these values with the value of f of 1, 1 equals 1 at the critical point. And then we can conclude that the absolute maximum value of f on D is f of 3, 0 is equal to 9, and the absolute minimum value is f of 0, 0, and figure 13 shows the graph of f of xy.